So this is the next in our pre-quantum mechanics section, and this one is on the Compton effect. So we just finished the photoelectric effect where we said you have a photon coming in, you have electrons popping off, and that was the equation that we had, the incident energy equals the energy it takes to free plus the kinetic. This is very low energy, so we can just use 1/2 mv squared. It's just that when you start to go, and we also showed that you could not, this would not work with a free electron right here. If you just had an electron here, this wouldn't happen. So at the higher energies, electrons and atoms appear freer and freer, and so the probability of occurrence on that surface right there drops when the energy goes up. And if that process drops, something else has to take place, and we said a process called the Compton process now starts to take over. And that's what we're going through right now, is the Compton process. So now what do we have right here? We have a photon going this way, runs into an electron. He's pretty much free now because this is, even though he's in an atom, this is going to be a lot higher energy. And since he can't deposit all of his energy and then give it all to the electron, that's impossible. So all he can do is ricochet off. So the photon hits it and then ricochets off this way, right here. It's, if we call this E gamma, we'll call this one E gamma prime. It's the energy he has after he bumped off the electron, and the electron's going to head off down in this direction, which we'll call E prime. Okay, and we'll say that the angle that the photon scattered was theta, and we'll say that this one is phi. This looks like a problem from momentum in classical mechanics, so we should probably look at momentum. This is the momentum of the gamma. This is the momentum of the gamma prime, and this is the momentum of the electron prime. And remember, we have a relationship. This is high enough energy. We are using relativistic equations. So we know that E squared is equal to P squared C squared plus M squared C to the fourth. So we can use that equation. Okay, well, let's go ahead and write out our equations then. First of all, let's write out the energy equation. The energy equation. Well, the energy before, we got E gamma. That one's not moving, so it's just mc squared. So we've got E gamma plus m of the electron, c squared. So there's the energy before. And then afterwards, it's just the energy of this plus the energy of that. It's just the energy of E gamma prime plus the energy of E electron prime. Okay, so there is our... Now, I guess we could use this equation right here and put them in terms of momentum. If we write them in terms of momentum, this equation right here becomes E of the gamma. Remember, for gamma ray, this is 0, so E is just P gamma C. So this is just P gamma C plus M sub E plus M sub E C squared equals the energy of this. Again, the mass is 0. That's a light right here. That's 0. So it's just P gamma prime C plus the energy of this right here. Well, this one has both terms, so it's the square root of both terms. So this one is the square root of P sub E prime squared C squared plus mass of the electron squared C to the fourth. So there's your energy equation. Well, we should look at momentum. we'll look at, since this is a two-dimensional problem, we'll look at momentum in the x. Momentum in the x. Well, before, it's all in the x. It's just p gamma. Afterwards, you just have the x component of each one. This one would be p gamma prime cosine theta. Plus the x component of this one, which is pe prime cosine of phi. Okay, so, and let me just, out of this equation, I think I'll just solve for this term. Why? Because one of the things I don't usually measure is the phi, and that's something I'll want to get rid of. So we'll solve for this term, pe prime cosine phi. It just looks like it's this minus this. P gamma minus p gamma prime cosine theta. Okay, and now we can look at the momentum in the y direction. P in the y. Well, it's 0 before the collision. And then I'll call upward positive, so you got p gamma prime sine theta plus, minus, because it's going down, we call that positive. So it's minus the momentum this way, which is pe prime sine phi. Okay, so there's all my equations. I might as well solve for pe prime sine of phi. Pe prime sine of phi. And that's just, these two are equal. I'll just move it to the other side. So this is p gamma prime sine theta. Okay, so again, one of the variables I want to get rid of is the phi. It's not an easy thing to measure, so we'll get rid of it. You notice here, I've got these two equations right here. If I square this and square that and add them, then I get a cos squared plus sine squared, which is a 1. So squaring these and adding them, this left side is just pe prime squared. Why? Because I get a pe prime squared cos squared theta plus pe prime squared sine squared theta. Factor out the pe prime squared. You got a cos squared plus sine squared, which is 1. So that's what I get so I'm squaring these two equations and then I'm adding them. Okay, and that should equal, it should equal this term squared. Well, if I square that term out, maybe I'll put the squares up there so you can see them. So what we're doing is we're squaring that, squaring that, squaring that, squaring that, and we're adding these two equations together. It's really all we're doing. Well, this first term squared is p gamma squared. P gamma squared. Then I got the middle term here, which is minus 2 times the first times the second. Minus 2 times the first times the second, p gamma prime cosine theta. Plus the last term squared, which is p gamma prime squared, and then cos squared plus p gamma prime squared sine squared. The cosine and the sine squared drop out, and this is just plus p gamma prime squared. Okay, so now I've got this equation and this one right here, because I've already used these two up right here. And so what do we want to do now? Well, we want to solve this, see this pe prime squared, I want to get rid of that. So I'm going to take that, pe prime squared, since we have these two equations, I'm just going to take that and put it right up into there. Okay, so then I won't have any pe prime squares anymore. Okay, before I do that, maybe I'll move this term over to this side So, because I'll probably want to square it right there. So let me first just take this term over to that side first. And if I combine it with this term, I can factor out the C. So that first term will be P gamma minus P gamma prime C. So that's what I get when I brought this over, plus the M sub E C squared. Okay, so that's the left-hand side, and that equals the square root term over there. Well, what we wanted to do, I wanted to square both sides. So I'm going to square this. And so then I only have what's inside the square root. So all I have is what's inside right there. And you notice I have a PE prime squared. What I'm going to do here is if I multiply everything by C squared, so if I put a C squared here, C squared, how about a C and a C? That's C squared, and a C squared. So this is all of that term right there. So what I have on the right-hand side is all of this, which is P gamma squared C squared minus 2 P gamma C, P gamma prime C cosine theta plus P gamma prime squared C squared. So that took care of all of this part of it right there. And then I have the plus the M sub E squared C to the fourth. Okay. So now I don't have any PE primes. So now we'll square this thing out right here. Okay, so if I square this thing out, I got the first term squared. Okay. This term squared would be P gamma minus P gamma prime squared C squared plus 2 times the first times the second M sub E C squared times this P gamma minus P gamma prime C plus this term, plus M squared C to the fourth, plus M sub E squared C to the fourth. And then on the right-hand side, I've got all those terms right here, which is a P gamma squared C squared minus 2 P gamma C, P gamma prime C cos theta plus P gamma prime squared C squared plus M E squared C to the fourth. Okay, so hopefully I can cancel some terms now. I have an M squared C to the fourth in both sides, so I'm going to cancel those two out. This cancels with that. When I multiply all this out right here, this first term, you notice what I'm going to get here is the very first term is a P gamma squared C squared. Then I got the cross term, minus 2 P gamma prime C squared, plus P gamma prime squared C squared. That's just this first term right there. Okay, well, I see there's a P gamma squared C squared on the other side. So this term cancels with that term. I have a P gamma prime squared C squared and a P gamma prime squared C squared over there. So that cancels with that term. Okay, so the only terms left I have is this term. I have all of that and that right there. Well, all three of those terms have a 2 in it. So I can cancel the 2's. I better write this out now. So what I'm left here on the left-hand side is I have this term minus P gamma prime. I'm going to move the C with each term, so it's P gamma C, P gamma prime C, minus P gamma C, P gamma prime C. So that's this term right here, and it's minus. Then I got plus M sub E C squared, P gamma minus P gamma prime, times, I'll put the C in with them right here. So it's M sub E C squared plus M sub E C squared. And we're left with, put this C inside, P gamma C minus P gamma prime C. P gamma C minus P gamma prime C. So that's the whole left-hand side. And the whole right-hand side is a minus P gamma C, P gamma prime C cos theta. Minus P gamma C, P gamma prime C cosine theta. Okay. I can multiply everything by a minus 1. I think that might be better if I make that a plus, make that a minus, make that a plus. Also, I can turn E gamma is just this, P gamma C, because there's no mass, and that's just E gamma prime. So I can turn all my PCs all the way through into E's. So this becomes E gamma prime minus M sub E C squared E gamma minus E gamma prime equals, and then we're using the plus, E gamma prime cosine theta. Well, what if we divide everything by the product, E gamma prime? If we divide everything, this thing is just left with a cosine. I'll put it over on this side. So we're left with a cosine theta. This, if I divide by that, is just a 1. And then we got minus M sub E C squared. And I'm dividing it by E gamma prime. Well, if I divide this by that, it's just 1 over E gamma prime. And if I divide that by that, it's just 1 over E gamma, minus 1 over E gamma. Oh, okay, so there is the Compton formula. Compton formula. Now, this isn't the one you're going to see in the book. Why? I don't know why they put that one in the book. If you actually do this experiment and you work with Compton Effect, you don't measure wavelength, you measure energies. How do you measure, how do you do this experiment? Well, you get out a detector. Just like we had a detector when we did the muons, we had what was called a scintillator. What happened? Any charged particle moving through there converts all of its kinetic energy into light. So let's say you have a radioactive source right here. It's emitting gamma rays right here. So you get their energy E gamma. That's the energy. Okay, and what are they going to do? They're going to come on in here. A lot of them will go through depending on the thickness, but every once in a while one will kick off an electron. So here's my electron, goes down this way. My photon is going to leave. It's not going to stay in there. Gamma rays are much more penetrating than electrons. The electron's not going to leave unless he'd have to have a ton of energy right here. He's not going to leave that. Okay, and here is my E gamma prime. E gamma prime right here. Okay, and what happens to all this kinetic energy right here? Well, all this kinetic energy, this electron's going to run into other atoms, eventually stop, and all of his kinetic goes, we hook up a little photomultiplier tube to it called a PMT. You get a little signal that looks like this coming out, and if you integrate that signal, you calculate the area of that, it tells you how much kinetic energy that had. Well, if we just look at this from an energy point of view, again, what was our energy? Before, we had E gamma plus the mc squared of that electron, m of the electron, c squared. Then afterwards, instead of writing it as all this square root, I think I'll just write it as this guy right here. Well, we have the energy of this, which is E gamma prime, but remember we have another way of writing the energy of an electron instead of that. We can just say it's the kinetic plus m sub e c squared. Well, you notice the m sub e c squares drop out, and so the kinetic energy looks like it's just this energy minus that energy. So it's just E gamma minus E gamma prime, right there. So I could, if I wanted to, I could have said E gamma prime is equal to E gamma minus kinetic, and I could have just put it up there and written it all in terms of kinetic energy too. Matter of fact, we could do that right there. We could say the cosine of theta is equal to 1 minus m sub e c squared. And what do we say E gamma prime is? It's just E gamma minus k. So you got 1 all over E gamma minus k minus 1 over E gamma. Okay, so what would you get here if you were to make a spectra of this? That is, on here, what you're going to plot out is the kinetic energy for each event. Each time you get a Compton scatter, you get the electron pops out, you get a signal, you integrate the area, that gives you a certain kinetic energy, and this will be how many of those you got right here. Well, we're not going to get any of them at E gamma, because K, from this equation, K has got to be less than E gamma. It's E gamma minus some stuff. So if E gamma is right there, the incident energy, none of these electrons will have that much energy. Matter of fact, if I just barely graze the electron hardly gets any energy if you just barely graze. It's like on a billiard table. If you just barely graze the ball, he doesn't get very much energy, so he's way over here someplace. If you hit him a little more square, he picks up a little bit more energy. Matter of fact, to give him the maximum amount of energy, what you want to do is you want to hit him head on right here, and then what way do you bounce straight back? So the most energy you can give to this electron is a head-on collision, and that would mean the angle is 180 degrees. You would scatter completely back. And so what you would get here is you'd get, these are bigger and bigger scatter angles until you hit 180, and then it would just drop off right there. So this is the theta equals 180, and these are all thetas less than 180 over here. They give a name to this edge right here. They call this edge the Compton edge. Edge right here. Arthur Compton actually, when he derived all this and proved it right here in the lab, he actually got the Nobel Prize in 1927, and this really cemented the idea that light is a particle. Okay, so you would get a spectrum that looks something like this. It drops back down. And we could figure out whether that edge is, because we just have to come back to here and plug in 180 degrees and solve for K. So if we do that, if you plug in 180 degrees, then that's just minus 1. So you get minus 1 equals 1. Minus m sub e c squared 1 over E gamma minus K. 1 all over E gamma minus K minus E gamma. 1 over E gamma. Well, if I want to solve for K here, I guess I better get a common denominator. So if we put in our common denominator, well, let's move this over to that side. So we got minus 2 equals minus m sub e c squared. And so my common denominator will just be the product of those two, E gamma times E gamma minus K. And in the numerator, I would have this, E gamma minus this, E gamma minus K. Okay. Okay, so now, well, this and this cancel out. And so this is just K right there. So we end up with, let's get rid of the two minuses. So we got 2 equals m sub e c squared. We just get K all over E gamma times E gamma minus K. Well, let's, I want to solve for K here. So let's move this up to this side. So we got 2 E gamma minus K equals m sub e c squared K. Okay, and then let's distribute this thing through. So we got 2 E gamma squared minus 2 E gamma K equals m sub e c squared K. Put this term over there and factor out the K. So you got 2 E gamma squared equals K times, if we factor that out, m sub e c squared plus 2 E gamma, or K, the maximum I can get from Compton scatter is 2 E gamma squared all over m sub e c squared. Remember, that's just a half an MEV plus 2 E gamma. So that we could say is for the Compton edge. Compton edge. Now, we're still going to get some photoelectric effect in here. And remember, we said the probability goes down, but you're still going to get some. Well, for the photoelectric effect, what would they look like over here? It wouldn't be this equation, because that's the Compton effect. Remember, with the photoelectric effect, all this energy goes into freeing it, and then the rest goes into the electron energy right here. Well, there is no gamma prime, E gamma prime with the photoelectric effect, and it only takes a few EV. So if this were a million EV, and it takes 1 EV to free up the electron, then he gets 999,999, which means he gets all the energy. And so what you would get is, you'd get a bump right there. These ones right here are due to the photoelectric effect. Photoelectric effect. These guys are due to the Compton effect right here. So this is the spectrum you would see for a detector like that. What if the detector had two different gamma rays coming out right here? Suppose it had one, like yttrium, you'll have one in the homework, yttrium 88 puts out 2 gamma rays, one at 0.9 and one at 1.8 MeV. Oops, sorry, that's 1.8 MeV. Well, what would just the 0.9 look like right here? If that is, let's just say there's 0.9, there's 1.8. Well, you're going to get a little bit of photoelectric, and then you're going to get the Compton. Remember, there's the Compton events right there. What about the 1.8? The 1.8, you get some photoelectric, and then you get some Compton right there. Well, what would you, then you just add those two curves together. If I add those two curves together, then I get something that looks like this, and then it went up. Oops, that doesn't look like a very good add. So I get this, and then it goes up, and then right here there's a bump on it, and then it even goes up higher another level right there. So there's the Compton edge for the 1.8. There's they call that the photo peak. This is the photo peak for the 0.9. This is the Compton edge for the 0.9 right there. So that's what you get right there. And when we look at our probability of occurrence, let's come over to here. Sorry. This process eventually starts to go back downhill right here. And another process is going to start taking off right there. This is actually called pair production. Pair production. What's pair production? Pair production is where the photon converts into an electron and an anti-electron. You get matter and antimatter. But you can see that this energy, just from energy standpoint, this energy of this photon has to be at least twice, because this has the same mass as that. So this energy of this photon has got to at least be greater than twice the mass of the electron, which is like greater than 1 MeV. But then it would have no kinetic. If you give it more energy, then you're giving it the kinetic. And so you know, it starts off at around 1 MeV, but it's not going to cross over until maybe 6 or 7 MeV. And I should also say that this cannot happen in free space. A photon cannot just turn into this. Why? Because from relativity, you notice, let's just say it goes off like this right here at equal angles, just to make it easy. Well, you could imagine Mary moving along with the same x value of this, and what Mary would see was she would see the two going straight up and down right here. And but she'd still say that's the speed of light right here. Everyone agrees on the speed of light, but you can see that momentum cannot be conserved. You cannot have something having x momentum and then no x momentum. So this cannot happen in free space. There has to be other atoms. You have to run into atoms, and then this happens right here. And then what's going to happen to this? One's an electron, one's a positron. Remember, this is an antimatter. He's going to slow down, eventually combine with another electron that's out here, and they form a little atom called positronium. Little E plus, E minus kind of orbiting, and then they decay. And all that energy goes into 2 gammas right here. It has to be 2 because you have to conserve momentum. A half an MeV and another half an MeV. So if you go out in space and look at for if you find any 0.5 MeVs in space, EVs, it's because positrons and electrons combined right here. And that just takes off right there. Okay, so now what I want to do is I want to show you some spectra right here, Compton spectra. And before I do that, here I have a cesium radioactive source, cesium. Cesium emits gamma rays at 660.662 MeV. So that would be, this energy is 0.662. If I wanted to figure out where this edge was, all I'd have to do is plug in 0.662 there, plug point squared, 0.662 there, and plug in a half right there, 0.5. And that would tell me where this edge is. Here I have a Geiger counter, and hopefully, if I just turn this Geiger counter up a little bit, it just takes a minute to warm up. But you can hear, first of all, you can tell these are photons. It certainly sounds like a particle right there. And it should even follow an inverse square law. Let me... So, but this thing has a half-life of 30 years. So if I just stood here for 30 years without moving anything, the clicking rate would be 1/2 of this clicking rate in 30 years. Right? So you can see this thing's going to last some time. Over here I have this is a Strontium 90 source. It's just an electron source. It doesn't give off gamma rays, it just gives off electrons. But electrons don't go through the material very well. So you can tell whether they put the source on this side of the disk or on that side. So if I put it on this side, now let me turn it around to the other side. So you can see there's a lot more electrons coming out of that back side and a lot less coming out of that front side. They just, for the gamma rays, they'd go right through everything right here. But electrons aren't that penetrating, see? So you can see it's... Okay, so now what I want to do is I wanted to show you here, all they do is count. If we could somehow measure the energy, this thing just counts it, measure the energy and plot it out, then we get a spectrum something like this. So let's... Okay, so now we have that spectrum for the cesium that you just heard clicking. This corresponds to the photopeak. These are all the photoelectric effect events right here. Here's my Compton edge. Now normally this would just take off like that, but it's the detector that cuts it off. So the detector just stops working above this level right here. But here you can see this Compton edge, and you can see the edge, if you plugged it into that formula, it looks like it's somewhere around the 450.45. Remember, we said this was 0.66 something was the photopeak. They call that the photopeak, Compton edge. Okay, moving on to, so now this one is a cobalt-60 spectra. Cobalt-60 actually puts out two gamma rays pretty close to each other. One's 1,000 or 1.173 MeV and one's 1.332 MeV. They're pretty close to each other. Those are, again, are the, we call from the photoelectric effect, the photo peaks right here. Here's the Compton edge, probably for this one, and you can see this another edge going up over here for the second one. And then this thing, again, the detector doesn't work below that level right here. So this would be cobalt-60. Okay, this is the yttrium, the one you had to do on the homework. Here, this one has the 0.9 and the 1.8 MeV. This is the photopeak for the 0.9. There's the 1.8. Here is the Compton edge for the first one. And there is the Compton edge for the second. Don't worry about anything below that spot right there. It should just keep going up. This is the detector effect right here. So you got photopeak, Compton edge, photopeak, just like before, another Compton edge right there. And so that's for yttrium. So this next spectra is from a very expensive detector. Borrowed it from a company. It was worth well over $1 million. And what this measures is just the background radiation in a room, in our lab, but it would be just the same here at RCC. What you're seeing is spectra from concrete and wood and everything else a building is made out of. And here you can see all these A lot of different events, a lot of different radioactive materials in there. You can see the most dominant one is potassium-40. I actually cut off the scale. It goes about 10 times higher. This is from concrete. We get most of our radioactive material from buildings from concrete. If you go onto a freeway, there's a lot of concrete on a freeway. A runway, there's a lot of potassium-40s right there. But you see all these other ones. This is such a good detector. I know what element is producing each one of these. And actually, this little bump right there, that little teeny bump right there is from weapons tests back in the 1960s. That's how accurate this instrument is. So, and then you see all these other ones. These are all the Compton events. And you can say, where's the Compton edge for this one? This is the dominant one. The Compton edge, if you plug it in, it's about right there. It's about almost 1.5. So you notice the background all of a sudden got bigger right there. And that little increase right there is the Compton edge due to that. And you can see when you get above 1.5 MeV, there's not many radioactive sources left. It's pretty much gone by then. So this section right in here is mostly good for the Compton effect. So if you wanted to measure gamma rays, a Compton instrument is the best way of doing it. But the only thing is, you just get a garble. These other ones are all the photoelectric effects right here. Okay, and one last one. So this spectra right here is taken from space. When I've flown an instrument, and actually a gamma ray instrument in space, measuring what are the energies of all the gamma rays coming from space. Now, the detector doesn't work below this line right here. Normally it just follows like an e to the -2 spectra right here. But you'll notice there is a big bump right there at 0.5 MeV. And that right there is from electrons and positrons running into each other at the top of the atmosphere. It's dominating our instrument right here. So again, this is what you'd get from just half MeV electrons and positrons annihilating with each other. Okay, so just to show you some spectra.